Welcome to Electron Line. Now in our quest to understand what a photon is, we're probably going to come now with this video to the most perplexing thing that a photon can actually do. It's probably one of the most perplexing things in the entire universe. A photon, which is a chunk of energy, a piece of energy that has no mass, can somehow convert itself into two particles that have mass. Wow. For example, a photon that has sufficient amount of energy, when impacting it on a target, so maybe like a small lead plate or something like that, if the conditions are just right, that photon will turn itself into two particles. Now it turns out when a photon turns itself into particles, it's usually a pair of particles, and the one particle is a particle and the other one is an antiparticle. So that's what we call pair production. So, with other words, an electron can be formed, and of course an electron is negatively charged and a positron is positively charged, so it will form an electron and the anti-electron called a positron. Now what's the difference between an electron and a positron? Well, it turns out they're identical in all respects, except one has a negative charge and the other one has a positive charge. So this is the electron that we're used to, and this is the positron, which is the antiparticle of the electron. Now what happens when an electron meets up with a positron? And they meet and merge together. Well, what happens is they annihilate each other and they will turn themselves back into a photon. Now, what is the energy required to turn a photon into an electron and a positron? Or if it was a very high energy photon, you could actually form a proton and an antiproton, or a neutron and an antineutron. Well, it turns out the amount of energy need comes from the equation E equals mc squared. So what is the energy required to make an electron, and what's the energy required to make a positron? Well, let's plug in the mass and multiply times c squared, and that will give us the energy. So to make one electron, for example, that would be equal to the mass, which is 9.11 times 10 to the minus 31 kilograms. And you multiply that times the speed of light squared, 3 times 10 to the 8 meters per second. You square that, and that will give us the energy required to make a single electron. So 9.11 e to the 31 minus times 3 e to the 8 squared equals, and the energy need would be 8.2 times 10 to the minus 14 joules. Now let's convert that to electron volts. So of course, to convert that to electron volts, that would be equal to 8.2 times 10 to the minus 14 joules, and multiply it times let's see here, 1 electron volt divided by 1.602. We're going to give it a few more significant figures to get a slightly more accurate value. And that would be times 10 to the minus 19 joules. So it's that many joules per electron volts. So divide this by 1.602 e to the 19 minus, and we get about 512,000 electron volts. So that's the amount of energy you need to make an electron, and of course that would also be the amount of energy you need to make a positron, because the positron is the exact same amount of rest mass. So the energy required here, energy for the photon, would have to be equal to 1,024,000 electron volts. Now, what if a photon came along that had more than that amount of energy? Well, then the additional energy would then be imparted on the electron or positron in terms of, or in the form of kinetic energy, and they would fly off at some speed. The more kinetic energy it have, the faster it would be flying away from this particular event. So, what kind of photon has enough energy, this many electron volts, to make an electron and a positron? So here what we can do is we can say, well, the wavelength would be equal to hc divided by the energy, and of course the energy is also in terms of electron in joules right here, so that would be equal to 6.626 times 10 to the minus 34 joules times seconds, multiply times c, 3 times 10 to the 8 meters per second, and divide by the energy for two of these particles. That would be 2 times 8.2 times 10 to the minus 14 joules, because we want to do it in joules to get the correct number here. So the wavelength would be, so 6.626 e to the 34 minus times 3 e to the 8 divided by 2 and divided by 8.2 e to the 14 minus equals, and so the wavelength would have to be, lambda is equal to 1.21 picometers, so times 10 to the minus 12 meters. And of course, that photon is so energetic that it falls in the realm of gamma ray. So we'd have to have a gamma ray photon to produce enough energy to create the two particles, but it can do so. Now that's quite amazing. Here we have a particle that moves at the speed of light. It has no mass, just energy, and it impacts on a target, causing it to change itself into two particles that actually have mass, one particle and one antiparticle. And then when those two come together, they annihilate each other and form back into a photon of the energy released equals mc squared for both particles. Just an amazing thing. How can a photon do that? Well, we don't know. We know that it does. And it just gives us another look, another window in understanding what a photon actually is. So if you're still interested, stay tuned and we'll take some other looks at what a photon can do, how through experiments we've understood the photon better and better, and eventually we'll be able to form a really good picture of what a photon is. And that's how we do it.